Let's now look at performance of our programs. Execution time for given input. So for example, I can measure the number of seconds that it takes. So my trusty iPhone 13 from the future takes 5 seconds to compute the eigenvalues of a web-linked matrix of size 1 billion by 1 billion, thus computing PageRank. Sounds impressive, right? Actually, that's not very useful information. I can't infer very much from it other than maybe I have a fast phone. It's more interesting to see how the time depends on the input size. I can use that to predict when I change the input size. So what I really want is a function and not a number. And it's even more interesting to see what happens when the input size increases without bound. Usually that's what I want to do. I want to increase the input size. And this is called asymptotic analysis. So what I want to do is do an asymptotic analysis. I want to know the function that gives the execution time as function of input size when the size increases without bounds. So this is a form of asymptotic analysis, which means to find an approximation whose error tends to 0 when a parameter increases without bounds toward infinity. If we know this function, we can infer many things. We can know what is the time for a given input. We can know what is the maximum input for a given time. We can even know smarter things like how much bigger things can I do if my computer is 256 times faster, for example. So computational complexity is the use of asymptotic analysis to study execution time and memory use of programs. Note the word complexity here is used in a different way from everyday life. So assume now f of n is the execution time in microseconds for an input size n. So my first question, what is the time for a given input size? So for example, if f of n is the function n, then if the size is 1, it takes 1 microsecond. If the size is 1,000, it takes 1,000 microseconds. And if the size is 1 million, it takes 1 second. That's fine. Now, if the function is 2n squared, these numbers are 2 microseconds, 2 seconds, and 23 days, 4 hours. It increases quite a bit. If it's n to the 4th, my function, then it's 1 microsecond, 11 days, 3 times 10 to the 10 years. And if it's 2 to the n, an exponential function, it very quickly becomes very large. So these red blocks here are a number of years that I really don't want to wait that long. I don't really want to wait 10 billion years to get an answer, or 10 to the 301,020 years. I don't want to wait so long. So there's a problem with these guys, 2 to the n and n to the 4th. We notice for big problems, we can't really solve them. We don't have the time. Let me look at now another question. What is the maximum input size for a given time? So if my function is 400n, then in 1 second I can solve problems of size 2,500. In 1 minute I can solve problems of size 150,000, and in 1 hour I can solve problems of size 9 million. But if my function is n to the 4th, these numbers are much smaller. Size 31, size 88, size 244. So again, n to the 4th and 2 to the n, they don't let me solve very big problems. In reasonable times, like 1 hour, I can only solve small problems. So there's something wrong with functions like n to the 4th and 2 to the n. Okay, let's think a little bit more now. How does the maximum input size, m, change if I buy a computer that's 256 times faster? So again, we use our functions. If we have 400n, if I buy this fast computer, I can treat problems 256 times bigger as before. If I have n to the 4th as my execution time, I can treat problems 4 times bigger. But if I have 2 to the n as my execution time, I can treat problems that are only plus 8. Notice in the first part here, I can treat problems bigger by a multiplicative factor. I multiply the size of the problems I can treat. These are all polynomials. Notice here the exponential function, I can only increment the size of the problems I can treat. So we can see there's something bad about the exponential function. Algorithms that take that much time have a problem. Notice also the constant factor doesn't matter. Between 400n and n, both of them is 256. Constant factors, depending on accidents of clock speed and so on, don't really matter. So in order to capture these intuitions, we want to have size increasing without bound. We want to ignore constant factors. We invent a new mathematical concept, which is called big O notation. So if my execution time f of n, we say it's big O of g of n. So fn has an upper bound g of n. So g of n is like the upper limit of how long the execution takes. And we can take into account that we're increasing without bounds and that constant factors don't matter. So the mathematical definition is here. So f of n is O of g of n. So if there's a constant c and a constant n0, such that for all n big enough, fn is smaller than g times n. So starting from a particular n0 here, beyond that point, fn will always be smaller than some constant times g. So it's bounded above by some constant times g. And we're not interested in the values of n0 and c, just that they exist. So that starting from some size and then bigger and bigger and bigger, fn will always be smaller than g. So that's what the big O notation means. So it captures our intuition. Let me now explain how it works with some examples. So here's a simple example. Suppose my execution time is 2n plus 10. Since 2n plus 10 is less than 4n for n greater than or equal to 5, this is actually O of n. So the g function is n. We can do another example with the same function, 2n plus 10. This is also O of n squared. Since n squared is growing faster than n, 2n plus 10 will also be smaller than n squared. So n is an upper bound, n squared also. Notice n is a good upper bound. N squared, it's an upper bound, but it's not a very good one. Another example, 2 to the 100, which is a huge number, many, many digits, is O of 1, which means it's a constant. It doesn't depend on n. So constants are constants no matter how large they are. Another example, we have a complicated function here, 3n squared plus 10n log to the base 10n plus 125n plus 100. This is O of n squared. In fact, the idea here is we can keep the dominant terms, so n squared, and remove all the constant factors, so the 3, and we keep n squared. Notice in all these cases, the function g of n is called the temporal complexity of the program.